When our company starts looking at virtualization and distributed computing, we have to adhere to a whole new set of standards and best practices, and it also raises a lot of new security concerns. Using virtualization, we can have many different servers or clients on the same hardware platform, that's the host. The virtualization software runs below the OSs and just above the hardware. Remember, that's the one we call ring -1. Often traffic between our clients or our servers may not have to traverse our network if they're on the same host. Some of the most common virtualization softwares could be VMware, Hyper-V, or Xen, and that's the software that sits between the hardware and the server OSs. So in virtualization, we have one host with massive hardware specs that would then carve up into smaller clients or servers. Distributed computing is to some extent the opposite. We use this if we have massive data sets or something that requires a ton of resources to run. Other than just running on our one system, we distribute the workload across multiple machines. This can be 1, 2, 5, 10, 100, 100,000 if we want. This is most commonly cloud computing, but we then need to ask the same question we always do: how do we ensure that the security posture of the local and remote clients are up to our standards? If we do use cloud computing, do they segment off our network? Many recent data breaches, for instance the one where a Republican consulting firm lost the user data of 200 million voters in the US, they had turned off a security feature that was enabled by default on Amazon Web Services. Obviously in this case the security was probably high enough, but had they gone through and analyzed what turning that feature off would do, they most likely wouldn't have turned it off. In every single data center I've worked in, there's been a big push to move to virtualization, get rid of all our physical servers, and it makes sense. Virtualized environments cost a lot less. We can quickly stand up new servers. We don't have to wait for the hardware. For the rack and the configuration, a full server build can be done in a couple of hours. You can easily take backups with snapshots, and server builds can be done with images. You can obviously do the same on a regular physical server. There's just so many more steps in between that has to be taken. You also have the ability to reallocate resources in an instant. Most SQL servers are really resource intensive. Instead of having to shut the physical system down, open the server up, add more memory, we can just go into the hypervisor, assign that server more resources, and there won't be any extended downtime. This obviously assumes there's resources available on the host. We can also in the supervisor allow servers to raise their own resources when they need. If a server is doing resource-intensive backups at night, it might need double or quadruple the memory for a couple of hours, and presumably most of the other servers are not using the memory at that time. We can either automatically, every night at 2 am to 4 am, double the resources, or we can just allow it to raise as it needs it. A large virtual host might use the power and cooling of, let's say, 10 servers. But if you then can house 50 or 100 or 500 servers on that one host, that's huge savings on power. That much smaller footprint will put out a lot less heat. We can then save on cooling as well. Many data centers use hundreds of thousands of dollars each month just in electricity. Being able to lower that as much as we can with virtualization is a huge incentivizer for senior management to pay for our virtual hosts. Looking at virtualization, the hypervisor is what sits on rings -1 between the hardware and the virtual machine. Looking at the graphics on the right, you can see a normal physical server would have hardware, then it would have an operating system on top of that, and then applications on top of that. Hypervisors, on the other hand, had a lot of stuff shimmied in between the operating system and the hardware. A Type 1 hypervisor, or bare metal hypervisor, is what you'd see in most data centers. They have a hypervisor engine on top of the hardware, and then on top of the hypervisor, all the virtual machines are built. These are the rack-mounted units. The common virtual servers are 2, 4, 8, or 12 rack units high. A rack unit is the standard measurement that pretty much anything that's rackable would adhere to. Each rack unit is 1.75 inches, or 44.45 millimeters. A regular physical server would normally be 1 or 2 rack units tall. So the virtualization host is obviously bigger, but you can house so many more servers on that smaller space. A Type 2 hypervisor is what many of us use on our own PC. We have the hardware, run our regular OS on top of that, then the hypervisor runs as any other application on our computer. That hypervisor has virtual machines that have operating systems. It's a much easier way for you at home to have multiple operating systems on one host. But in a data center, that structure would make no sense. It's just another layer eating up resources. You do, however, for the exam, need to know the difference between Type 1 and Type 2 hypervisors, as well as how they differ from a regular physical server. Up till now, we've talked a lot about how virtualizing our servers is cheaper, smarter, more efficient, and just all around better. It does, however, also present a whole new group of vulnerabilities. This is partially because the technology is pretty new, but it's also very complex. So when we design the layout of our virtual hosts, We need to ensure that the security posture and the design is done right, so all the clients should be from the same network segment. One virtual host should only have clients on the internal network, for instance, or in the DMZ. They should never have clients from both. And we need to ensure that all the clients are logically separated, just like we would with any physical server on a network. We would have HR VLANs, accounting, IT, procurement, and so on. And in systems, when you have different trust levels or different security levels, it's smart to segment those security levels on their own VM host. This is another way we can minimize VM escape or virtualization escape. That's when an attacker can jump from one client to another client on the same host. We obviously wouldn't want this at all. It's much worse if an attacker can jump from a server that has a secret label onto a server with a top secret label, than if they just can jump from secret to secret. And just like anything else we do, we want the layered defense, where an attacker needs to get through multiple defenses, not just a couple. How we secure the hypervisor itself is also a concern. The hypervisor sits below all the clients. It's possible if an attacker gets access to the hypervisor, they can access all the clients. So we need to ensure that the hypervisor is secure enough, and we have enabled all the security features it has that make sense to us. Another threat to virtual host is oversubscription. It's easy to assign more CPU or more memory to more systems, and forgetting to look at how many resources are left on the host. It's also often a money concern. Virtual hosts are expensive. So maybe we can squeeze just 5 more or 10 more servers on it before we need to buy another one. And a lot of times it can run okay for a week or 2 or a month. But at some point it will reach a stage where all the resources are used, and then some. Every single application hosted on clients on that host will slow down. Then all of a sudden your funding request for the new virtual host will get a lot more attention, get a lot more traction. But as good IT professionals, we want to be proactive. We want to keep an eye on the resource utilization on our VM host so we know when we're getting close, and we know when we need to recommend to management that need to add more resources on new hosts. And you will most likely not be the person with a hands-on virtual servers, but you need to understand how they work and how they're going to impact you. If everything is oversubscribed, it's going to slow every server down. It can cause server crashes. Now it's impacting our availability. Crash can compromise the data. Now it's impacting our integrity. So while you're not the hands-on virtual server guy or girl, you need to understand the tremendous impact they have on all the stuff that you do. Cloud computing is one of those terms that you're going to have to explain to people over and over who don't really understand what it is or how it works. To them it's just a cloud, or well, you just upload it to the cloud and then the cloud take care of it. Then you very nicely explain to them that there is no cloud. It's just someone else's computer somewhere else. For us, using the cloud is just our organization building or outsourcing part of our IT infrastructure, storages, or applications. And there's a ton of good reasons to do that. Most of those are cost related. It's cheaper to have someone else do it. They probably have a larger data center. They're more specialized in doing that one thing than we are. There's a lot of instances where it makes much more sense to have someone else do it for us. Cloud computing can really be divided into 3 main areas. Private cloud is us building and running our own cloud infrastructure, or paying someone else to do it for us. We need to be very clear here, this is not Amazon Web Services or something like that. The private cloud solution we have, it's built and hosted just for us. Public cloud is what 99% of cloud solutions are, is shared tenancy. A company builds a massive infrastructure and rents it out to anyone who wants it. Amazon Web Services, Microsoft, Google, IBM. They pretty much have pre-configured images for everything you want. So to stand up a cloud server, it's just a lot of next, and then choosing the sizes, disk, memory, whatever else you want of resources, the operating system, and in less than 10 minutes you can build a server. And depending on your plan, you pay for the OS, utilization, the traffic, and whatever other parameters you have in your contract. But compared to physical servers, it's much cheaper. Hybrid cloud is a mix of private and public cloud computing. We can, for instance, choose to have a private cloud for all our sensitive information, and then use public cloud for anything that's non-sensitive. And with cloud computing, just like any other outsourcing we do, we want to make sure that we have the right to audit, pen test, conduct vulnerability assessments, and to ensure that the vendor's in compliance with the industry we're in and the standards we need to adhere to. Most of the large cloud providers have much stronger security than you would need for most standards, HIPAA or PCI DSS, but you still need to do your due diligence to ensure that they actually do. In a private cloud, we obviously own everything. There is no demarcation between us and a vendor, whereas in public cloud, there is a very clear demarcation. Depending on the type of service we have, we're responsible for both the data and the security of certain segments of the servers. If you look on the graph here on the right, you can see non-cloud, but it would be the same for private cloud. We're responsible for everything. The dark blue indicates what we're responsible for. IaaS, or infrastructure as a service, the cloud provider provides everything up till the OS. We add the OS and everything on top of that. So they have the data center, the networking, the storage, the servers, the virtualization, and then hands it off to us. They're responsible for everything below that and the security on that. We're then in turn responsible for the operating system, the databases, the security on that, and the applications. Software as a service, or SaaS, the vendor pretty much provides everything except the data. These are very common solutions where we have a vendor application integrated with our systems. We would then manually enter the data on the SaaS page, or it can get pushed for some of our other applications. Many of the environments I've worked in, we've had hundreds of applications that were software as a service. Before we'd allow traffic from our system to theirs, they'd go through a security accreditation. But really, the application could be anything. It could be Gmail, Office 365, Dropbox, payroll. It could even be security appliances. The important part really is we need to make sure that it's secure enough for us before we start sending traffic and accepting traffic from that software. And lastly, we have PaaS, or Platform as a Service. Here you can see the vendor provides us everything except the applications and the data. Think of it as a freshly installed version of whatever operating system you would want, and we install whatever we need on there. They're responsible for everything below the applications, and that includes the security at each stage, and then we're responsible for the application and its security. For the exam, I'll take some time and understand the differences between the different kinds of public cloud. I don't really recommend memorizing anything. It's much more important to understand how they work. Many of the questions on the exams are procedure-based. In this situation, what would you do? If you just understand the facts and not how the things work behind them, you may not do as well. At least be able to explain to someone else what the difference is between infrastructure, software, and platform as a service, and where and why you would use the different ones. I briefly touched on grid or distributed computing earlier, and what it really does is it uses the resources not in use on hundreds of thousands of computers to perform very complex tasks. Each computer or node gets a smaller set of subtasks, but if you all of a sudden have 100,000 computers compute power, it can be tremendously powerful and really fast. The biggest legal network I know of grid computers is the BOINC, or the Berkeley Open Infrastructure for Networking Computing. Currently has over 4 million machines enrolled, and they're used on a lot of different scientific research projects. And because they have so many machines enrolled, they have solved problems that would have taken them hundreds of years just with their own computers. And Berkeley actually has some of the most powerful computers in the world. Peer-to-peer or P2P is similar but very different. In this structure, any system can be both a client and or a server. And most people probably know them from the torrent networks where people share music, movies, programs, pictures, or whatever. Going back to the intellectual property we talked about earlier, most of this is done without the copywriter's consent, so it is technically illegal. In some of the older versions of the peer-to-peer networks, you would have centralized indexing servers. Anyone wanting to disrupt the peer-to-peer network would just have to take the indexing servers down. The current versions, however, use decentralized infrastructure. Every single client is also a server, and it has the server index. If we have a network of 100,000 peer-to-peer servers, someone takes down 10,000 of those, the net will just be 90,000, there'll be no other impact. Whereas before, if you took 5 or 10 indexing servers down, the whole network would be gone. We can also use virtualization for thin clients. The reason we call them thin client is because, well, all the hardware is not there, or the full application isn't installed on it. It's not a full client. We can either use diskless workstations or diskless node. It'll have all the same hardware and firmware as a regular PC would, but it doesn't have a hard disk. All it has is the BIOS that, just like on a regular PC, would perform the post or the power on self-test. Then it downloads the kernel and the higher level OS. Most of them just log into a virtual server on a virtual host. Whenever the computer is not in use, that client is shut down, doesn't use resources. Whenever you power your PC on, the client is spun up and it starts using resources. But it can be a great way to be more secure, as well as assign resources where they're needed. Thin client applications are applications that run elsewhere. Everything's executed there. You don't have a program on your computer, but you use a web browser login, and everything you do is executed on that server.